Hi, so now we'll be starting a new chapter which is called Inequations and Equations. So in the last chapter that we had covered, we had looked at quadratic equations, and along with quadratic equations, we'd also seen the idea of quadratic inequalities. So now we want to kind of build up on that and look at more slightly more complicated equations and inequalities. We'll be basically starting by looking at what is known as the Wavy curve method, which is essentially used to solve a large category of rational inequalities. We'll follow that up by introducing the modulus. Now, the modulus as a concept is very, very important from a competitive exam point of view. A lot of equations and inequalities that are asked in competitive exams, especially the JEE Advanced and the JEE Mains, do involve modulus at some level or the other. So we'll be introducing the modulus and be looking at plenty of equations and inequality that involve the modulus, the use of the modulus operator. We'll also be looking at situations wherein you have square roots or radical signs present in an inequality, and we'll be basically looking at what are the basic essential things that have to be taken care of at that when you're dealing with inequalities involving square roots, etc., or cube roots for that matter, or any radical signs. And towards the end, we'll also be introducing the idea of the concept of logarithms and look at equations and again inequalities based on logarithms, right? So before we kind of start with the Wavy curve method, we just quickly want to look at some very simple, the very basic set of rules as far as inequalities are concerned, which are some basic steps which are frequently involved in solving inequality, especially. Right, so the first, these are very straightforward ideas which are frequently involved when inequalities come into the picture, but at the same time they're kind of frequently used, so we have to be careful about it. So the first, so we are assuming that we have two numbers A and B such that A happens to be the smaller of the two values. So these three things have to be taken care of. The first statement, what we are saying is that you can always, if A is less than B, then that will automatically also imply that A plus K is less than B plus K. K over here could be any real value, which means it could be positive or it could also be negative. So what you're essentially saying in the first statement is that if you have an inequality and you add or subtract the same constant on both sides, then the sign of inequality will essentially remain the same. So again, addition and subtraction of the same constant on both sides can always be established without really worrying about anything. When it comes to multiplication or division by a non-zero constant, then you have to be very careful about one thing, whether the constant happens to be positive or negative. So if A is less than B and K is a positive constant, then A times K will also be less than B times K. So if you have an inequality in which, and you, what can always be done is you can always multiply both sides or divide both sides by a positive constant. And when you do that, the sign of inequality will remain the same, right? So as a simple example, if I'm saying that 2x minus 4 is less than 3, I can equivalently say that x minus 2 is less than 3 by 2. So what I've done over here is I've divided by 2 on both sides, and the sign of inequality remains the same. And of course then I could add 2 on both sides. Right, so the solution set of the original inequality therefore effectively is that the value of x must be less than 7 by 2, or if we use a bracket notation, x belongs to the set minus infinity to 7 by 2. Right? Multiplication and division by a constant which is negative is something which you have to be very, very careful of. Whenever you have if you have an inequality and you choose to multiply or divide both sides by a negative non-zero constant, that can again, by a negative non-zero value, that can again be done under the condition that but what you have to kind of be very careful about is that the sign of inequality in such an operation will reverse. So if you start with a statement that A is less than B and I multiply both sides by K, where K is a negative value, then the sign of inequality will reverse. So A times K will be greater than B times K, right? So again, as an example, we're taking simple examples for the timing just to illustrate the idea. So if I have this inequality, I can basically multiply both sides by minus 1. So this becomes 2x minus 1, this becomes 4. But then again, since you multiplied by minus 1 throughout, you will have to reverse the sign of inequality. So that turns out to be the solution set. So the set of values that x can assume is x can be any value which is greater than or equal to 5 by 2. And again, if we go back to the bracket notation we are introduced in quadratic equations, x can belong to the set 5 by 2 to infinity. Right, so these are three basic manipulations that have to be taken care of. A second and a very, very important point that has to be taken care of, especially when you're solving equations, and which is something that I've already mentioned in quadratic equations, is that whenever you're solving an equation and you have a statement of the form AB equal to AC, do not jump to the conclusion that B must be equal to C. That is to say that do not just blindly cancel out that common factor on both sides and say that B is equal to C. B equal to C is only one of the possible conclusions. Another conclusion could obviously be that the common factor, which in this case is A, happens to be 0. So your conclusion from such a statement should always be of this form, that either the common factor is 0 or B is equal to C. Right? So given a common factor on both sides and you're solving an equation, what your approach should be to say that either that common factor will be 0, take that possibility, or it is not 0. And if it is not 0, obviously you can cancel it out on both sides and then look at what is, and then look at the reduced form. Cancelling a factor on both sides is nothing but really dividing by that factor on both sides, and that is allowed only as assuming that the common factor through which you are dividing both sides is a non-zero value. This is very important when you're solving equations, because if you don't, if you kind of in a hurry cancel out the factor on both sides, there's a very good chance that you might miss out on certain solutions. So as another example, right, so suppose this is our equation and I factorize both sides. So the left hand side is x minus 1 into x squared plus x plus 1. This of course can sort of as. So now if in a hurry I just cancel out x minus 1 on both sides, I'll get a reduced form which will actually not give me which will give me an incomplete solution set. So the right way to proceed from here again will be that to say that okay, there is a common factor x minus 1 on both sides. Either that factor is 0 or it is not 0, and if it is not 0, I can divide by it on both sides, and this is what I'll be left with. Right, so from here x is equal to 1, and from here right, so this then will be your complete solution set, 1 comma root 3 comma minus root 3. And of course, if you had cancelled out x minus 1 on both sides before, then you would have only been left with root 3 comma minus root 3, which would then have been an incomplete solution set. Right. So with these basic ideas now, I think we can start with the Wavy curve method. So the Wavy curve method is essentially used in solving inequalities which fall into one of these, let's say, 4 categories. Over here, f of x and g of x themselves are some polynomial functions. That makes f of x by g of x a rational function. So you have a ratio of polynomials on one side, and on the other side you have 0. And again, in terms of sign of inequalities, you could have a greater than 0, less than 0, greater than equal to 0, or less than equal to 0. So given any inequality of this form, we can then try to apply the Wavy curve method. It helps us get the solution set. There can be a lot of variations in the complexity of such problems, and essentially what we do is we try to develop a set of rules following which we will be able to solve the inequality. So some simple examples over here. This of course is a quadratic inequality only. You have a product of two linear factors over here. Again, your f of x and g of x are over here. F of x and g of x are over here. Right. So for a majority of the questions, we'll be applying the Wavy curve method, wherein f of x and g of x can be or are already in a factorized form. That is to say that they have been expressed as a product of linear factors. The linear factors may have corresponding powers associated with them. That is to say that the linear factors might be repeated. So over here, for example, I'll say x plus 1 is a twice repeated linear factor, x minus 1 is a thrice repeated linear factor, and so on. Right? And of course, there can be a situation in which you might have the linear factors in the denominator. There can also be situations in which we might have quadratic expressions which are not getting factorized further into real linear factors, which means that maybe you could have maybe you add x squared plus 1 over here. Right, so over here what has obviously happened is that x squared plus 1 cannot be factorized further into real linear factors. So even such a situation can happen. So again, in the Wavy curve method, we'll be essentially be discussing a set of rules which help us solve such inequalities. And of course, we can have a large category of problems in which the inequality might not be directly in this form, but is easily reducible to this form by some manipulation. So as a simple example, if you have, so this inequality itself is not in one of these four forms, but by some basic manipulations of getting all the terms to one side and taking a common denominator, etc., we can reduce it to one of these four forms, right? So again, this is something that we'll be looking at in detail. Again, for such problems, we'll be seeing that it is not very you cannot just trivially multiply both sides by x minus 1 and then rearrange them. There are certain things that have to be taken care of, right? So the plan henceforth will now be to basically start with simpler cases and build up the set of rules that we'll be considering, right? So in our first set of simple cases, we'll be considering rational inequalities in which we only have non-repeated linear factors in the numerator. That is to say, non-repeated over here means the power of associated with each of the linear factors is 1. And for the moment, we are assuming that we are only considering situations in which g of x happens to be 1. So there aren't any terms in the denominator. So as you can see in all these four problems, what's happening is essentially that you have all the inequalities consist of a product of linear factors, which are, for example, for the first two examples, the linear factor is already the whole expression is already factorized. In the third case, this middle term will have to be factorized further. Similarly, over here, this term will have to be factorized further. So as a first step, so for such problems again, what is the sequence of steps that we'll be following? In the first step, we want to factorize the expression as far as possible. And in all these examples, you are being able to get you're being able to factorize it completely. So for the first one, it's already in a factorized form. So that is okay, right? So step one will be to get to resolve all the expressions into linear factors as far as possible. As a second step, we want to ensure that the coefficient of x in each linear factor is positive. Right? So the first three steps that we always strictly have to follow are these. First of all, of course, assuming that we've already got it in factorized form, we want to reduce the inequality to a form in which the coefficient of x in each linear factor happens to be positive, right? Now, in some cases that might already be the case, like the first problem. In some cases that might not be the case, in which by simple manipulations you can always reduce it to this particular form. So, for example, in the second problem, 2 minus x, the coefficient of x happens to be negative over here. So what we can simply do is take a minus 1 common and then multiply both sides by minus 1. Right? So these manipulations are pretty straightforward. But you would want to reduce the inequality in a form again in which the coefficient of x in each linear factor that is present happens to be positive. In the next step, what we'll be doing is we'll be finding the set of what we'll be calling critical points. Now, critical points for us are the set of roots of each of the linear factors. So basically, you'll be equating each of the linear factor present on the left hand side, let's say, to 0, and the corresponding values of x that we get is basically the set of critical points, right? So in step 2, we'll be finding a set of critical points, which are basically the roots at which each the set of critical points basically corresponds to the set of roots of the linear factors present, right? And in the third step, what we'll be doing is we'll be plotting each of the critical points on the number line. For example, if you're solving it for x, you're plotting it on the x-axis and so on. So let's do that. Let's follow these steps for the first question and then look at the last step that has to be used. Right? So let's call this expression as some y. So the coefficient of x in each linear factor anyway is positive. It's 1 and 1, so that is okay. Then what are my critical points over here? The root for this linear factor obviously is minus 1, and for this factor is 2. So I'll plot these values on the number line. So that's the third step taken care of. The final step in the first category now is that what we'll do is this. since there are two critical points over here, those 2 points will divide the entire number line, the x-axis, into 3 intervals. So those intervals can be thought of as the set of values of x less than -1, the set of values between -1 and 2, and the set of values which are greater than 2, right? Similarly, if there had been 3 critical points, you would have got 4 intervals. In general, if you have n distinct critical points, you will be land up with n plus 1 intervals. Now the idea is that as long as you have ensured that the coefficient of x in each linear factor is positive, what we'll now do is we'll go to the rightmost interval and draw a wave which approaches the x-axis from above, right? And we will make the wave cross this x-axis at each of the critical points. So now the wave by default comes from above, from the rightmost interval. So you come from here, cross at 2, cross again at -1, and go back up, right? So again, as long as you've again ensured that the coefficient of x in each linear factor is positive, go to the rightmost interval, from above the x-axis draw a wave which will approach the x-axis, and at each critical point it will now cross the x-axis. So we'll first cross at 2, go below the x-axis, then cross again at -1 and go above the x-axis. Now the idea is, if I call this expression as y, so again just imagine the normal x versus y plane. The idea is that just like in the case of quadratic inequalities, the set of, you want y to be positive, and y will obviously be positive when the wave, when the graph is above the x-axis, right? So the set of, the interval where the graph is above the x-axis constitutes the set of points where the expression is positive. So we'll put a positive sign over here. Similarly, over here between -1 and 2, the expression becomes the curve wave goes by. I shouldn't use the term graph. In this case, the graph this is also reflective of the actual graph. It's similar to the actual graph, but in cases where we'll be adding linear factors to the denominator, then in that case, using the term graph we should not really use the term graph for the time being. So the wave, wherever the wave is above the axis, the expression will assume a positive sign, and wherever the wave is below the x-axis, the expression will assume a negative sign. So you get a positive sign over here, a negative sign over here, and a positive sign over here again. That is essentially the interpretation of the wave. So this was our inequality in the final form. So we want it to be positive. So for that, we'll have to see where the wave is above the axis. That clearly is happening for values of x which are less than -1, or values of x which are greater than 2. So x can take a value which is less than -1, or x can take a value which is greater than 2. So that's basically my answer. Again, let's go over the sequence of steps that we had said. The first thing that we wanted to ensure was that the coefficient of x in each linear factor is positive. That was already the case. The set of critical points turned out to be -1 and 2. We plotted them on the x-axis. From the rightmost interval, we got a wave which approached the x-axis from above, and then made it cross the x-axis at each of the critical points. This idea of making the wave approach from above the axis, as with respect to the rightmost interval, will necessarily be true only if you've ensured that the coefficient of x is positive in each linear factor. If you haven't done that, then it is not really necessary that the wave will approach from above the x-axis. But as long as you have ensured the first step, that was that the coefficient of x needs to be positive in each linear factor, then by default you can kind of make your wave approach the axis from above. So and now the good thing about this is that you can keep extending it. It doesn't really matter on the number of linear factors that are present. You can keep extending it. Assuming for the timing, of course, that they are non-repeated. So for the second part again, this is the inequality. But then again, now the coefficient of x in the second factor is not positive. So we'll have to transform this inequality. So this is now the transformed inequality. And again, I'm referring to this entire expression as the variable y, suppose. So y happens to be equal to 2x minus 1 into x minus 2. So again, critical points would be coefficient of x is positive in both the factors. Half, 2 are the critical points with the wave. From the rightmost interval comes from above, crosses at each critical point. Right? So now again, you want the whole thing to be less than or equal to 0. So the value that x can take will have to lie between half and 2. And here, because equal to 0 is also allowed, we will also be including the critical points. Right, so the answer for the second part is that the value of x has to lie between half and 2, inclusive both of half as well as 2. In the third problem, we had an x square minus 9, so I have factorized it as x minus 3 into x plus 3. So again, you have a product of 4 linear factors over here. As a first step, again, the coefficient of x in each linear factor is positive, so that is okay. Second step, identify the critical points, minus 3 by 2, 3, minus 3, minus 3 by 4. Plot them on the number line. So I'll get minus 3, then we should get minus 3 by 2. And again, we'll kind of do the same thing. From the rightmost interval, get your wave from above and make it cross at each critical point. So the expression to be less than or equal to 0. So for less than 0, obviously, what x should lie between minus 3 by 2, or and since it's a less than or equal to 0 is also allowed, so I'll be including the critical points also. Obviously, if x takes any one of the endpoints also, the expression will be equal to 0, and the sign of inequality will be the inequality will essentially be satisfied. If you want to use bracket notation for the answer, for the last one again, we have a quadratic expression which is not in factorized form, but you can easily factorize it. Right, so over here we have a product of 5 linear factors now, and let's again, coefficient of x in each linear factor is positive, so that's taken care of. Critical points will be half, 1 by 4, 0, minus 2, 5 by 2. So plot them on the line on the x-axis. Since we had ensured that the coefficient of x is positive in each of the linear factors, from the rightmost interval we'll get a wave from above. So to be greater than or equal to 0, for the expression to be greater than or equal to 0, the wave needs to be above the x-axis, and it's a greater than or equal to 0 case also, so the critical points will again be included. So answer should be between minus 2 to 0, or between or any value greater than or equal to 5 by 2. So the first case that we have essentially seen, in which you have inequalities, in which you have something of the form f of x greater than 0, less than 0, greater than equal to 0, less than equal to 0, where f of x is essentially a product of a finite number of non-repeated linear factors. It's pretty straightforward. Now in the second variation, what we'll be doing is we'll also now additionally be adding linear factors in the denominator, right? So in our second variation, we are essentially looking at rational inequalities, in which we have, the rational function consists of non-repeated linear factors in the numerator as well as the denominator. These problems now, again, the earlier steps that we had talked about kind of remain the same, that you'd again want to factorize the numerator and denominator as far as possible. In each linear factor, you'd want to ensure that the coefficient of x is also positive. Now, and a couple of additional things that happen over here is now, a couple of additional things that we have to take care of are that we'll now obviously also have critical contribution to the set of critical points from the denominator. So the total set of critical points will consist of critical points from the numerator and also critical points from the denominator, right? Look at the first inequality. There are 2 linear factors, and the factor in the denominator, the coefficient of x is not positive. So I'll have to kind of manipulate it a bit so that now the coefficient of x is positive in both the linear factors. The idea will now be to take the critical points from the numerator and denominator and again plot them on the line. So a very basic point that we now always have to, additional step that has to be taken care of, is that the critical points from the denominator can never be included in our final solution set, right? This is very, very important. Any critical point which comes from the denominator can never be included in the final solution set. The reason for that simply is that if you, for example, in this inequality, if I say that x equal to 2 if I let x to be equal to 2, then what will happen essentially is that the denominator will become 0. And that, as I mentioned before, is never allowed. Whenever you're solving equations or inequalities, you never ever allow the denominator to become 0. Right? So essentially this is pretty much the only additional step that has to be taken care of when non-repeated linear factors are present in the denominator, and that is that again, that critical points which come from the denominator must never be included in the final solution set. So now if you want to basically just to help you keep track of that convenient way, just to keep track of which are the critical points from the denominator. So one thing that we could do is, when marking the critical points, around the critical points which come from the denominator, we could just mark a ring around them. So that'll just help us keep track of the fact that which points happen to be from the denominator and which points happen to be from the numerator. Everything else will remain exactly the same. So in this case, again, this is my final inequality form, right? So this is the expression. So I'll draw the wave. In this case, it's anyway a less than 0 case, so the answer should anyway be that x has to lie between. If this had been x minus 1 upon 2 minus x should be greater than or equal to 0, that would have transformed to x minus 1 upon x minus 2 should be less than or equal to 0. But even in that case, it has to be kept in mind that you would not have included the value 2. So then the answer for that particular problem would have been that the values of x should be greater than or equal to 1 and they should be strictly less than 2. So again, for the second category of problems, just to repeat, the previous steps remain the same for the first category. The only additional thing now is that you will be getting critical points from the denominator also. We always have to keep this idea in mind, that critical points from the denominator must never be included in your final solution set. Just to help us keep track of which are the points from the denominator, we can visually just mark a ring around the values which come from the denominator. This of course is not really an essential step. It will just help you keep track of the critical points which come from the denominator. Everything else essentially remains the same. So for example, again what we can do is first factorize the numerator and denominator separately. So this is the final form of the inequality. Right? Now again, there will be a total of 4 critical points over here. So 2 and 3 come from the numerator, and over here minus 2 and minus 1. So, and minus 2 and minus 1 come because of the denominator. So we'll just quickly mark a ring around it. Coefficient of x was anyway positive in all the linear factors. So we'll draw a wave. What I would like to stress at this point itself is that the wave that we've drawn over here is not the graph of this function, right? So the wave is just a convenient trick that we are using to help us solve the inequality. This visually is not the graph of this. If I define this as my function f of x, this is not the graph of the function f of x, right? So this is something you have to be careful of. So again, for the expression we want it to be less than or equal to 0 now. Now here's what you'll have to be careful about. For less than or equal to 0, again the wave needs to be below the axis, right? It's a less than or equal to 0 case, which means that you can also include the value. So for example, at least to start off with, I'll say that the intervals are minus 2 to minus 1, or x can lie between 2 and 3. But now we have to be very careful. Critical points which correspond to the denominator, which are minus 2 and minus 1, can anyway not be included. So that is already, you can't include those points. But if you look at the values 2 and 3, which are the critical points corresponding to the numerator, right? Over here, what is happening is that since it's a less than or equal to 0 case, x can obviously be equal to 2, or you can also allow it to be equal to 3. If x is equal to 2 or x is equal to 3, the expression becomes 0, and obviously the inequality is satisfied. So you will be including the numerator points over here. Both the numerator points, in fact. So the final solution set is this, that x can lie between minus 2 to minus 1, or it'll have to be greater than equal to 2 and less than equal to 3. If I want to use the bracket notation, I can say something like this. It is again important to remember that the points, the critical points which come from the denominator, can never be included in the final solution set. In fact, as a rule, what you can also easily, if you want to generalize, you can also say that critical points, again, corresponding to the denominator should never be included in any of these forms. As far as critical points corresponding to the numerator are concerned, when will you include them in the final solution set? Only if it's a greater than equal to 0 or less than equal to 0 form, right? If it's a greater than equal to 0 or less than equal to 0 form, you will include the points from the numerator, but obviously not from the denominator. And if it's a strictly greater than 0 or strictly less than 0 form, you will not include points from the numerator as well as not include points from the denominator. Third problem, there are 3 factors in the numerator, 3 factors in the denominator. First, again, we want to ensure that the coefficient of x is positive in each factor. Now, in this case, there are actually 2 factors in which the coefficient of x is negative. So effectively what will happen is you will take a -1 common and a -1 common. So effectively the sign of the inequality will remain the same. Sign of inequality overall remains the same because effectively there are 2 linear factors and both the factors had a negative coefficient. So if you take a -1 common, you kind of get cancelled out. Again, if I just quickly plot down all the critical points, so what all do I get? I'll get 0. Then we have 3 by 2 and sorry, over here we have the same factor on both sides. So let me just change the problem a bit. Let's make this x minus 2. 3 by 2 and 4 by 3. So 4 by 3. Sorry, there's a 3 by 5 also. These are the critical points: -12, 3 by 5, 0, 3 by 2, 4 by 3, 2. Right? And the factors from the denominator are -12, 3 by 5, or 2. Expression to be greater than or equal to 0. So the wave needs to be above the axis, and it's a greater than equal to 0 case. So we will be excluding points from the denominator, but including points from the numerator. So our final answer should be x belongs to the set -infinity to -12, -12 not included, union 0 to 3 by 5, 0 included, 3 by 5 excluded, union to 3 by 2, and finally union 2 to infinity excluding 2. Right? We've seen the intervals where the wave is above the axis. That's -infinity to -12, 0 to 3 by 5, 4 by 3 to 3 by 2, and 2 to infinity. Of these endpoints, 0, the points corresponding to the numerator will be included. So 0, 4 by 3, and 3 by 2 are included, and the points corresponding to the denominator, those are -12, 3 by 5, and 2. Those points have been excluded. Right, so we've seen the 2 cases till now. First case, we essentially saw linear factors which were only present in the numerator, and then additionally we also saw a situation in which you can have non-repeated linear factors either in the numerator or and also in the denominator. In the third case, what we'll be doing is we'll also be considering the possibility that the linear factors present in the numerator and denominator may have powers other than 1, right? Or in other words, the power could be 2, 3, or anything else. So essentially, you have repeated linear factors present in the numerator or denominator. So again, the steps that we've already discussed will still hold true, which means that first you'll see whether each linear factor, after factorizing to the best extent possible, you'll have to check whether each linear factor, the coefficient of the variable x is positive in each linear factor or not. If it is not, then reduce it to a form in which the coefficient of x is positive. In the second step, what we'll be ensuring is that again, we'll be looking at the critical points and then from the numerator and denominator, plotting them, plotting our wave, and And again, as we discussed, in our final solution set, critical points from the numerator must never be critical points from the denominator must never be included. If it's a greater than equal to 0 or less than equal to 0 case, critical points from the numerator will also be included. If it's a strictly greater than 0 or strictly less than 0 case, critical points from the numerator will also have to be excluded. Right? So now the additional steps would be that, again, depending on the situation, you will be looking, each linear factor itself will have a certain power, it may have a power other than one associated with it. Right, so the only additional step that will be required would be this, that suppose the factor x minus a raised to n happens to be present either in the numerator and denominator, so x equal to a obviously becomes the critical point. Now depending, and we'll obviously be plotting it on the number line. So now when the wave reaches x equal to a, you'll have to check whether n is even or odd. If n is odd, like in the case that we were, for example, in the original first two cases, we were anyway considering non-repeated factors, in which case the power was 1. So that kind of comes under the case that n is odd. So if n is odd, like previously what we were doing previously, you will just have to ensure that the wave crosses over to the other side. If it's coming from above, it will go below. If it's coming from below, it will go above. Whereas if n is now even, then the wave will get reflected at that point and kind of bounce back, get reflected back on the same side. So if the wave is kind of coming from above and the power n is even, it will kind of bounce back. Right? And if n is odd, it will cross. So this is the only additional. These are the only additional steps that you kind of have to take care of, right? So again, when corresponding to the critical point x equal to a, if this is the factor, when the wave reaches x equal to a, if the power of the factor is odd, the wave will cross over to the other side at x equal to a. And if the power associated with the factor is even, it will get reflected at that point, and it will kind of get reflected back on the same side. It will bounce back. So let's just look at some application of this. Right. So in the first case again, we have some linear factors in the numerator and denominator. They have different powers associated with it. So first step is to ensure that the coefficient of x in each linear factor needs to be positive. That automatically already is the case. And we'll now be plotting each of these critical points. So minus half, minus 1, minus half, right? So plotted the 5 critical points, of which 3 by 2 and minus 1 are from the denominator. Right. So this is something which we have done up till the second case. So now ideas from the third case. So again the wave will come from above. Now the factor corresponding to 3 by 2 is over here, and if you see it has an odd power, so you'll make the wave cross over to the other side. At 1 again the power is odd, so it will again cross over to the other side. At 0 now, if you see that there is an even power associated. Since the power over here is 0, you will make the wave reflect at 0 and will kind of bounce back to on the same side. So it was coming from above the x-axis, it will kind of get reflected at 0 and go to the same side. Then at minus half, it's again an even power, so it will again bounce back. And at minus 1, it's an odd power, so it will cross. Right? So this should now be the wave that we want to deal with. Again, came from above from the rightmost interval. At 3 by 2 the power was odd, it crossed. At 1 again the power was odd 3, it crossed. At 0 the power was 2, even, so bounces back. At minus half the power is 4, again even, bounces back. And at minus 1 again the power is odd, so it will cross. Right? So now again we want the expression should be greater than or equal to 0. Since it's a greater than equal to 0 case, we need to include critical points from the numerator and obviously exclude critical points from the denominator. So what should our answer be? X can lie plus, 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 plus. Minus 1 to minus half. Now effectively, since minus half, 0 and 1 are being included, I can simply, this effectively means that I can include all points from minus 1 right up till effectively this means that x lies between -1 to 1, excluding -1, including 1, union. So in the second question again, we have 5 linear factors, and the coefficient of x in each linear factor is positive, so that is already taken care of. And so again, we just first plot the critical points. -2, -half, 1/3, 1 and 3. Of these, -half and 3 come from the denominator. At 3, the power is odd, so you'll cross. At 1, the power is even, so bounces back. 1/3, it is odd, crosses. -half, it is even, bounces back. -2, it is odd, so crosses. Right, again, come from the rightmost interval, come from above. At 3, odd power, cross. At 1, even, bounce back. 1/3, odd, cross. -half, even, bounce back. -2, odd, cross. Right. So now we want the expression to be less than or equal to 0, right? So I can include critical points from the numerator. Here this is 1/3, 2, 3 effectively, including 1. 1 is anyway has to be included, so I don't have to consider separate intervals. Right, so that should be a final answer. In this problem again, first we'll kind of have to factorize the whole thing. So I'll take a -1, since the coefficient of x over here is not negative, is negative, I kind of need to change it to a positive coefficient. So I'll take a -1 common, so I'll get a -1 cube. Once I get a -1 cube, I can kind of, I'll effectively get a -1. So when I cross multiply on both sides by a -1, right? So this is now the form of the final inequality. So again, there are 1, 2, 3, 6 linear factors present. Linear factors present, again, plot the critical points. Now we have to be careful. X minus 2 actually has an overall power of 5, so we can just come in. So -5/2, -2, right? The critical points from the denominator over here are -5/2 and 3/2. Now the power corresponding to 3 is even, so it will bounce back. Corresponding to 2 is odd, crosses. Corresponding to 3/2 is again odd, crosses. Corresponding to -2 again is odd, so crosses. And corresponding to -5/2 is even, right? And now we want the expression to be strictly positive, so we'll have to be careful about something like that. Now, for it to be strictly positive, we have to now also exclude critical points from the numerator, right? So x can lie between -2 and 3, right? So the answer again should be, we want a positive case. -2 to 3/2, union 2 to 3, and union 3 to infinity. You have to be careful that, don't express this interval as 2 to infinity, because you cannot include the points 3, you can't include 3 either. Critical points from the numerator as well as denominator both have to be excluded. So this will be the final answer. So one last variation that you want to introduce in the Wavy curve method is this, that is a situation wherein you might have a quadratic expression which is not factorizable. By not factorizable, what I mean is it is not factorizable into real factors. So we already know that this will happen when the b square minus 4, the discriminant value of the b square minus 4ac value is negative. So suppose you have an expression of the form ax square plus bx plus c present either in the numerator and denominator, where b square minus 4ac happens to be negative. Then what is to be done? If you recall from what we had discussed about the sign of a quadratic expression, we had basically seen that when b square minus 4ac is negative, what that essentially means is that the sign of the quadratic expression will always be the same, right? So in fact, if you remember, we had seen that if d is less than 0, then the graph of this function will be a parabola which will never intersect the x-axis. And if a is positive, it will always be above the x-axis, and if a is negative, it will always be below. What that essentially then means is that as far as the sign of the expression is concerned, it will, this such a term, where again when assuming that b square minus 4ac is negative, such a term will contribute a positive sign if a is positive, and will contribute a negative sign if a is negative. And since in solving an inequality, we essentially, and therefore as far as such a term is concerned, when you have 0 on one side and on the other side you have your rational expression, if ax square plus bx plus c is present, what you can simply do is, if a is positive, you can replace that entire expression by +1, and if a is negative, you can replace the entire expression by -1, right? But one thing that has to be taken care of is that this is only applicable when you have 0, when you have an inequality of the form f of x by g of x greater than 0 or less than 0 or greater than equal to 0 or less than equal to 0, right? That is to say that all the terms, that there has to be a rational expression on one side, and on the other side you need to have a 0. So for example, if I have this situation wherein I have this inequality x minus 1 upon x square plus 1 is greater than 1, over here now, this idea is not applicable. You really can't say that since x square plus 1, the b square minus 4ac value is negative, then I just simply replace it by 1. However, if the inequality is x minus 1 upon x square plus 1, if you have x minus 1 upon x square plus 1 greater than 0, then of course this is applicable. So I can simply replace x square plus 1 by a is positive, so I'll replace it by 1. Right. It's easy to see why this works out. Basically, what you are again saying is that since in x square plus 1, since the d value is negative and the coefficient of x square is positive, therefore x square plus 1 will always be something which is positive. And since it is already positive, you can multiply by it on both sides. That's what's essentially happening. Right, so these problems can easily be dealt with now. In the first inequality, now x square plus x plus 1 clearly cannot be further factorized into real factors, because again the d value over here is -3. So I can replace x square plus x plus 1 by 1. Similarly, so now again if we look at x square plus x plus 2, this particular factor, the b square minus 4ac value is negative and the coefficient of x square is positive, which effectively means that x square plus x plus 2 is always going to be positive, and therefore I can effectively divide by it on both sides. So I can replace, again now it's a usual Wavy curve method problem, so -3 by 2, 2 and -3 by 2 come from the denominator, 2 it is odd, it will cross, 1 it is even, it will bounce back, -3 by 2 it's again even, it will bounce back. Right? So you again want the expression to be greater than or equal to 0. So now we'll have to be careful about this. So for greater than equal to 0, obviously you can consider the interval 2 to infinity. And also, as we've discussed, you also have to include every critical point from the numerator. So the point 1 also has to be included, since it's a greater than equal to 0 case. The third one, 3x square plus 2x plus 1, again the d value is negative, so I can replace this by +1 since coefficient of x square is positive. And if I look at this factor, the d value is again 1 minus 4, that's again negative, but the coefficient of x square over here is negative. So I'll replace this particular term by +1 and this particular term by -1. So I can obviously multiply by -1 throughout, and consequently the sign of inequality will be reversed. Right, so at 1 it bounces back, it will cross at half and again cross at -3 by 2. You want the expression to be greater than or equal to 0. So the final answer should be, these two intervals can of course be combined. So my final answer is, right, so we've in detail seen a lot of cases in which the Wavy curve method can be directly applied. One other thing that you want to look at is that you might have inequalities on which the Wavy curve method is not directly applicable, but which can easily be reduced to a form wherein the Wavy curve method will be applicable. So, right. So suppose you have inequalities of this particular form: f1x by g1x is greater than f2x by g2x, g2x, where again f1x, f2x, g1x, and g2 of x are some polynomial functions. So again, a rational function greater than or less than or greater than equal to or less than equal to another rational function. Now the problem over here is that as we have discussed before, the wavy curve method is essentially applicable where you have a rational function on one side and 0 on the other side. And of course then you go on to follow all the steps in which the rational function is, you kind of create, factorize the whole thing into linear factors and then follow all the steps. So over here the wavy curve method as such is directly not applicable. Before I generalize, let's just look at an example. Also, what is not very obvious is that you can't simply just cross multiply throughout. So as an example, so as a first point, so for such inequalities you can't simply just say that f1x into g2x is greater than g1x into f2x. So as a simple example, if I say 1 upon x minus 1 is greater than 1 upon 2 minus x, and then I go on to say that okay, 2 minus x must be greater than x minus 1 and therefore 3 is greater than 2x and therefore x is less than 3 by 2. That is incorrect. This is incorrect because of the fact that when you are multiplying, when you're doing something like this, that I multiply throughout by x minus 1, as we have seen that multiplication, when you multiply both sides of an inequality, it really becomes important whether that expression by which you are multiplying that inequality, whether that expression is positive or negative. Now, when I multiply by x minus 1 on both sides, the problem is that x minus 1 as an expression could be positive or negative or even 0 perhaps. So when that multiplication is done, I cannot just keep the sign of inequality the same. Same argument goes for 2 minus x, right? So of course there can be a situation in which there is an expression which you know that that expression is always positive, or you know that that expression is always negative. Under such circumstances, you can obviously multiply by such an expression. So if it had been a 1 upon, for example, if it had been a 1 upon x square plus 1 greater than 1, suppose. In this case, you could have very well multiplied throughout by x square plus 1 because specifically you know that x square plus 1 happens to be positive all the time. But again, as I said, in general, you will not do that. So the typical strategy in such problems is to get all the terms to one side, right? So for example, I can shift all the terms to the LHS, for example, so that you get 0 on one side. And then you go on to simplify, let's say, the LHS by simple multiplication and get a common denominator. And finally, you again have some rational function on the left hand side, which can again you'll kind of go on to reduce it in terms of linear factors, right? So now we can kind of go ahead and apply the wavy curve method and get the answer. So as I said, in the previous example, so as we had discussed, you cannot simply just cross multiply on both sides. So what I can do is get all the terms to one side, which if I simplify, I get something like this. Right? So now this of course becomes a very standard form on which you can directly apply the wavy curve method. So again, from what we've discussed, there are 3 critical points. 1. Right, so our final answer will be of the form of this particular form. This should be our final answer. X can either lie between 1 and 3 by 2, or it will have to take a value which is greater than 2. So again, the main point that I'll re-emphasize again is that if you have an inequality of the form rational function greater than equal to, less than or less than equal to another rational function, you cannot in general just simply cross multiply. You will have to get all the terms to one side, simplify that entire expression, and then apply the wavy curve method. So once you reduce it to the form some rational function greater than or less than 0, or greater than equal to or less than equal to 0, you can then go ahead and apply the wavy curve method. Let's look at another example. So again, if this is my inequality, I'll have to first try to simplify it. Again, please don't make the mistake of just cancelling out the common factor on both sides. Get all the terms to the left hand side, suppose. Right? We can simplify this further. Right, and of course this 2 doesn't really matter, you can divide by 2 throughout. So there will be 5 critical points. 1, 2, 4 and 5. Right? We want the expression to be positive. So the wave should again be above the axis. So x can lie between 1 and 2, or between 5 by 2 and 4. Or again, we just simply cross multiply by x minus 1 all on both sides. Simplified the left hand side on RHS. There was a common factor. We made sure to not cancel it on both sides. Got all the terms to one side, simplified the expression till we just were left with linear factors. Of course, again, as we've discussed before, you could have been left with a quadratic expression which is not getting factorized further. But the idea again is to get reduce the inequality to the form rational expression greater than or less than greater than equal to 0 or less than equal to 0, and then just simply follow the steps that we have discussed with respect to the Wavy curve method. Right, so that finishes the Wavy curve method. In fact, in your book, in the equations and inequations booklet that you have, the first 5 CCPs, CCP concept 1 to concept 5, will involve exercise which will essentially involve different variations of the Wavy curve method. So now you're in a position to try all those problems. Right? Thank you. In the next concept, we'll be essentially introducing the very important mortalis function, which again, as I talked about, which again I had mentioned that it happens to be very important from a equations and inequality point of view. So we'll be introducing that in the next lecture. Thanks a lot.